This interview is part of the History Heard project. The content of this interview may be used for historical research. However, no part of the video itself may be reproduced without the express written permission of an authorized History Heard representative. Today is July 19th, 2012 at 3 p.m. This is an interview with Dr. Richard Gatti in Los Angeles, California. He was born on January 12th, 1937 in Hoboken, New Jersey.
There may be a time when there'll be a universal stem cell. I can kind of envision that in the not too distant future. There's somebody in this building working on that kind of a more for bone marrow stem cells than for all stem cells. But we now have the tools and we're learning so much. I've only gotten back into stem cell work in the past year because of this other project that we may or may not talk about. We're just trying to get some neurologic stem cells derived from patients with AT so that we can test the new drugs we're designing for them on specifically AT cells to look to see, one, if they're potentially harmful to neurologic tissue. There's no good way to test any drug on neurologic tissue right now. So the FDA would be very impressed and interested in a methodology that would allow drugs to be tested on nerves and neurologic tissue, right? So that's one thing that would come out of this immediately. And secondly, we want to be able to correct. We think that ataxia is a neurologic disease, that we know. The cerebellum's involved in the back of the brain. That's very clear from looking at autopsies, and today you don't even need it, or you can see it on MRIs or CAT scans. You can see that the cerebellum is much smaller than it should be in these children. As they grow older, the cerebellum shrinks even more. So we know that that's our target for drug therapy. And we're designing the drugs so that they're small enough to get into the brain and hopefully do something in the cerebellum. Now, we're trying to create a disease in a dish, so to speak, a model of ataxia telangiectasia. So we took these cells from the patients by fibroblasts, and there's methodology of just the past 2 years where you can take someone's skin cells and convert them backwards. You can de-differentiate them or reprogram them back into what's called a pluripotential stem cell. So that's a step back. Your skin cells can only make more skin cells. They can't go back and make bone marrow cells.
Right.
But if you transfect them with certain viral constructs, if you put back certain genes, and we know which genes, we may not know all of them, but there are 4 that are crucial. And that's what I talked about at Harvard Westlake. If you go put those in, the stem cells revert, they reprogram back to a cell that now remembers how to make more than just skin cells.
Wow.
And beyond that, then, you can put them in culture, and by some other tricks, you can now coax them in the direction of making neural cells. So you've gone backwards, now you're going to go forward in a different pathway. And we're doing this work specifically on AT cells so that we can go back and correct what the deficiency is. Now, we haven't found the deficiency yet in the laboratory neural cells. We have different kinds. We can coax them to differentiate into astrocytes and oligodendrocytes. And we kind of know where we want to go with that because it's the Purkinje cells in the cerebellum that are most depleted in these patient cerebellums. That doesn't mean those are the target and that they're the inciting problem. It could be that they deteriorate because the cell that nurses them or feeds them or controls them is at fault. Okay? That's anterior grade degeneration. Or it could be that a cell that they report to, the Purkinje cells, reports to a cell that is defective. And if that cell dies, they die because they have no one to talk to anymore.
Right.
That's retrograde neurodegeneration. Could be either, or it could be the central one. So it could be A, B, or C. By isolating these individual cells in the test tube, we hope to find out which ones look the most abnormal. Now, that's never the same as doing it in the animal, but we can go back to animals when we have a hypothesis. First, we need to build a hypothesis, and we can test the drugs along the way to see which drugs correct, they abrogate whatever the findings are, that, you know, the abnormalities that we find. So that's what we're doing in stem cell work, but it's really to test the drugs. But to go back to the other thing, I can envision now where we could make any kind of a stem cell from any patient, and it doesn't take that long. I thought this was going to take years, and we do this in weeks.
Wow. Oh, really?
Oh, you have to work quickly because the cells differentiate so quickly that if you don't do the experiment this week or next week, by the following week, they've already moved on. They're changing, they're growing up, they're differentiating. And then you're not doing the same experiment anymore. You're doing another experiment that may or may not be relevant to what you're trying to do. You see? So this whole area it's a very dynamic area of working with stem cells. And we've learned all of that in the past 2 or 3 years.
It's incredible.
Yeah, it's really incredible.
Thank you so much. I don't want to